All right, in this video lesson, we're going to take a look at a classic Newton's second law problem, which is dealing with an elevator. The concepts that we cover in this video are going to be applied to many situations, but particularly we're going to be looking at the elevator and how an elevator works. And hopefully everyone that's watching this video has experienced an elevator once in their life, so you can kind of use some common sense and logic to help us with the physics concepts as we go through. So to start off with some general kind of concepts or experiential knowledge from an elevator, let's start off thinking about how we feel when an elevator is stopping and when an elevator is starting. Because when you are on an elevator and you're at rest, or when it's kind of in motion already, you feel normal. But when the elevator is starting or stopping, you kind of feel different. And so we're going to really rely on those feelings that you've had on an elevator to help us with what's going on with the physics. So let's first start off with the first point, which says when you're starting going up or you're stopping going down, you feel blank. Now I really want you to think about that. Maybe even pause the video if you want to think about kind of how you have felt. But when you get on an elevator and you are starting going up, so you step on the elevator on the first floor and you're going up to the 10th floor. Okay, so you're starting going up, and at the same time, okay, you're going to have the exact same feeling when you are stopping going down. So that's where you are maybe going back down towards the first floor and you stop. In both situations, I want you to think about how do you feel on the elevator. Do you feel heavier or do you feel lighter than your normal self? Hopefully, you were able to guess from experience that you feel heavier. And we're going to talk about that later on and kind of put the physics to it as to why we are feeling that way. But hopefully your experience has taught you that when you are starting going up, so you step on an elevator on the first floor and you go up, you feel heavier. And when you're going down and you're stopping, you also feel heavier. So you can probably guess what the second one's going to be, but let's kind of think through that situation as well. When you're starting going down, so you step on the elevator on the 10th floor and you're wanting to go down. When the elevator starts moving, or when you're stopping going up. So you're going up to the 10th floor, you're at floor 8, floor 9, and then all of a sudden you stop. Okay? In both those situations, hopefully you can kind of go from your experience and say, I feel lighter. So once again, let's kind of think through that. When you're starting going down, so I step on the elevator on the 10th floor and the elevator starts going down, you feel lighter. Or when you're stopping going up. Okay, so you're going up, floor 8, floor 9, all of a sudden the elevator starts to stop, you feel lighter. Now, hopefully your experience jives with that. If you've had different experiences, maybe, I don't know, you're defying physics, or maybe it's just been a while since you've been on an elevator. But I challenge you to think about next time you're on an elevator how you feel. Now, why this is going to have is going to do with Newton's second law, but it also has to do with Newton's first law as well. And remember, objects want to keep doing what they're already doing. So keep that in mind as we go through this video. Now, a convention in physics when we're dealing with elevator problems is to make up the positive direction. Does that mean you're going to get the answer wrong if you make down positive? No, but just so you know, typically we make up the positive direction. So that's something that you're going to want to make sure you do, so you're kind of on the same page with what I do in the video. Okay, so let's kind of recap a little bit on the next two slides what we just said. So this first image that we see right here, this is a situation where you're feeling your normal weight. And so when you're on an elevator, when do you feel your normal weight? Well, there's two times. When the elevator is at rest, or when you're already in motion, or in other words, constant velocity. So in other words, you're going to feel your normal weight when the elevator and you together are in equilibrium. Now, when you feel greater than your normal weight, is when we've already gone over this, is when you're in motion where this elevator is going in some sort of an upward motion or upward acceleration. So we've kind of covered that on the previous slide. There's two times that you're going to feel greater than your normal weight. And that is when you start to go up and when you are stopping going down. Now, we're going to cover this later on, but since it's already on this slide, let's cover this now. What is this blue arrow referring to? Well, you may be thinking, oh, it has to do with the motion of the elevator. Well, that's actually false, because right here, we feel heavier or greater than our normal weight when we're stopping going down. So why would the elevator be going up if we feel heavier going down? So this arrow that's at the very top right here has nothing to do with the motion, but instead it's an acceleration vector. So what we can deduce is we are going to feel heavier when our acceleration vector is pointing up. Now on the next one, the third part there, we're going to feel less than our normal weight when we start to go down, or when we stop as we're going up. And think about in that situation, whether you're starting to go down or you're stopping as you're going up, same thing for that. In both, the acceleration is going to point down. And then in the last one, and we're going to take a look at an example here, is that if you were in the unfortunate situation where the cable breaks on an elevator, which, by the way, that rarely ever happens because elevators are very secure, so if you have a fear of that, don't worry. But, you know, in this hypothetical non-real physics situation where the cable did break, how would you feel? Well, in that case, you would feel weightless, and we're going to talk about why you would. So, what I want to do before we start getting into some problems is I'd like to look at those four separate situations. Stopping going up, starting going up, stopping going down, and then stopping, starting going down and stopping going down. Okay, so stopping going up, starting going down, stopping going down. I know that sounds very confusing, but we're gonna take each of those separate situations one at a time, and we're gonna make sure we understand from a physics point of view why it is you feel heavier and why it is you feel lighter. A couple things before we start. First of all, you'll notice a big red arrow on the left side of the screen, and you'll notice that it's facing up. Please do not confuse this with the actual motion of the elevator. This red arrow is designed to tell us which direction is up. And remember, in the physics conventions, we always want to make up positive. It's just easy to stick with a convention and be consistent with it. So the red arrow just tells us that any vector pointing up will be positive and any vector pointing down will be negative. The other thing we need to understand before we move on is, where do you get this idea of feeling heavy or feeling light? Okay, so why would you feel heavy and why would you feel light? Most people, their first guess is you feel heavy or you feel light because of gravity. So they think that if you feel heavy, you've got a really big gravity, and if you are feeling light, you have a really small gravity. And that's not true. And think about it. In Unit 4, how did we calculate force of gravity? Well, we calculate force of gravity by taking our mass times the acceleration of gravity, which is g. Well, does your mass ever change? No. And does the acceleration of gravity on Earth change? No. We're still going to always be at 10. So it's not gravity that's actually changing when you're feeling lighter or heavier. What is changing is the surface that you're on, which in other words is force normal. So when you feel heavy, it's your force normal that is greater than force gravity. Now when you feel lighter, it's your force normal that is less than gravity. So in other words, it's the surface that's pushing into you that makes you feel heavier or lighter. So I'm going to keep that up there to the top right so we can kind of refer back to that when we need to. Okay, so what we're going to do right now is we're going to look at these four separate situations, and we're going to draw some force diagrams and use Newton's second law to kind of help us figure out, from a physics standpoint, what's going on here. Okay, so one thing that I think is going to really be beneficial for you is to kind of do a little review of what we looked at in Unit 3. We were talking about velocity vectors and acceleration vectors and speeding up and slowing down and all of that. So what I want us to do is I want to look at every single situation, and I want to look at what is the sign of our velocity and then what is the sign of our acceleration. I really feel like this is going to be beneficial so you really get a full picture of what's happening here. So remember, velocity is what direction of motion you're actually going in. Velocity goes with motion. Okay, so let's go through each of these situations and look at what is the sign of our velocity. And remember, vectors that are pointing up are positive, vectors that are pointing down are negative, according to the red arrow that's on the left. All right, we're just going to focus on velocity. So for the first one, stopping going up. Now, what does stopping have to do with anything? It's acceleration, right? So I don't care about stopping right now. All I want to know is which direction am I going? I'm going up. So if I'm going up and I've said that up is positive, then my velocity is positive. Let's look at the one right below. Starting going up. Once again, I could care less about starting. That has to do with acceleration. I don't care about that. What I care about is the fact that the elevator is going up. And so in that case, velocity is still positive. Let's look at the ones on the right. Starting going down. I only care about going down, and since now the elevator is going down, the velocity is negative. For the fourth one, stopping going down. Once again, don't care about stopping. All I care about is going down. And so that means my velocity will be negative as well. So now I know the signs of my velocities for all four situations. Now let's go back through and think about what the accelerations would be. Okay, for the first one, now I do care about whether or not I'm starting or stopping. All right, so stopping implies that the elevator is slowing down. And remember, when you're slowing down, the velocity and acceleration vectors have to be opposite. So if I'm stopping and my velocity is positive, my acceleration must be negative. Let's look at the one below. I am starting, which means I'm speeding up. If the object is speeding up, the velocity and acceleration have to have the same sign. So for starting going up, if my velocity is positive, my acceleration also has to be positive. On the ones on the right, the velocity is negative and I am starting. I'm speeding up. Okay, so don't get so bogged down with the going down. Remember, negative is just the direction. Negative just means it's going down. So if I'm speeding up and my velocity is negative, my acceleration has to be negative. It means both vectors are pointing down. If I'm stopping and I'm going down, okay, stopping is slowing down. So if my velocity is negative, my acceleration needs to be positive in order to make that object slow down. Okay, so now what I'm going to do is to the left of every single elevator picture, all I'm going to do is I'm going to draw in my velocity vectors and my acceleration vectors. So let's do velocity first. For the first one, velocity is facing up. Second one, velocity is still facing up. Third one, velocity is facing down. And fourth one, velocity is facing down. Remember, positive is up, negative is down. Now I'm going to go through and I'm going to draw my acceleration vectors. For the first one, acceleration is negative, so that's down. Second one, acceleration is up because it's positive. Third one, acceleration is down because it's negative. And then fourth one, acceleration is up because it's positive. Once again, confirming, notice when the vectors are facing opposite directions. So in situation 1 and in situation 4, when they're facing opposite directions, what is the elevator doing? It's stopping, right? And then in situation 2 and in situation 3, when the vectors are facing the same direction, they're going to be speeding up or starting. Okay, so now that we have that basic understanding and that review down, we can now start to look at how do forces play into all of this. Okay, so what we're going to do is we're going to draw a force diagram for every single one of these elevator situations. So my elevator and me, we're all one system, and we're going to represent that with a dot. Okay, now what I'm going to do is I'm going to draw in my vectors. Think about when you're standing on an elevator and you're going to draw the force diagram for you. Okay, because we care about what we are feeling. We don't care about what the elevator is feeling. We care about what you are feeling as the rider of the elevator. So what forces are acting on you as you stand on an elevator? Well, the obvious, force gravity. And remember, we've covered that force gravity is constant. Your force gravity does not change in all four situations because your mass is constant and your acceleration, your g, is constant. So I'm just going to draw in force gravity for every single one. And they're all going to be the same length because the value is the same. It doesn't matter force gravity because they will always be constant. What does change is the force normal, what the surface is actually doing underneath your feet. Okay, so that's actually what's going to change, and that's what's going to make us feel heavier or lighter. All right, so hopefully you've kind of already figured out that when you are riding an elevator and you're starting and stopping, that you are not in equilibrium in the y direction. You are experiencing an acceleration, and therefore, when we add the normal force to the gravity force, it should not equal zero. Either the gravity has to be greater or the normal has to be greater. Okay, so let's look at the first one. We are stopping, going up. Right away, I already know in all of these situations that force normal is going to point up. Force normal is going to point up because the ground beneath you, the elevator beneath you, is pushing against your feet. All right? We need to know, is the force normal bigger or is the gravity bigger? And there's two ways you can think about this. The first way is the conceptual way. Okay? And remember, objects in motion want to stay in motion. Okay? So think about you. You are stopping, going up. All right? So you're on the elevator, going constant velocity. You get near to the top, and all of a sudden, the elevator starts slowing down. What does your body want to start doing? It wants to keep going up, right? So it's almost like, imagine you're kind of lifting off the ground a little bit. You know, obviously not a lot because you're not levitating, but you're lifting off the ground a little bit. And so does the ground exert force normal greater than gravity or less than gravity? And hopefully you would be able to figure out it would be less than gravity. So remember, when you are feeling lighter, your normal is less than gravity. So normal, I'm going to put 1 slash, and gravity, I'm going to put 2 slashes. Now, there's a physics way to actually solve this problem. If you're not doing well with the conceptual stuff, you're like, I don't really know how I feel on an elevator, that's confusing to me. Don't worry, there's a physics way behind this. We're going to use Newton's second law to help us figure this out. Okay, remember, Newton's second law is looking at the net forces acting on an object. In this case, the net force is your force normal plus your force gravity. Now remember, I said in the last video that your net force and your acceleration will go in the same direction. They're always pointing the same direction. So we've already established that acceleration is negative. And remember, in elevator problems, negative is down. So if your acceleration is down, your net force must also face down. And the only way in this situation to have the net force face down is if gravity is greater than normal. And just so you can see that with some numbers, let's make some numbers up. Let's say force normal was 5 newtons. Gravity maybe was something like 10 newtons. So you would have a force net of 5 newtons facing down. From here on out, I'm going to use the physics method to explain the force net rather than the logical. But if the logical works well for you, continue to do that. Let's look at situation number 2. You're starting going up. Look at your acceleration. The acceleration is positive. Which direction is positive, up or down? It's up, right? So if up is going to be where your acceleration is, then up also needs to be where your net force is. So we already know that force normal is going to point up. In every situation, the ground has to push you up. The question is normal greater or is gravity greater? And in this case, if you want the net force to be, or excuse me, the acceleration to be up, then you need to have the force net be up, and that means the force normal has to have the greater value. Notice when force normal is greater than your gravity, you are going to feel heavy. Let's look at the last two. Situation number 3. Your acceleration is negative, which means it's down. And if your acceleration is down, your force net has to be down. So we have force normal again, but acceleration is down, and so our gravity has to be greater than our normal. And then finally, in the last one, stopping going down, our acceleration is positive, meaning that's up. So since acceleration is up, your force net has to be up. So when we draw force normal from the ground, pushing up on the person, we know force normal has to be greater than gravity. And when force normal is greater than gravity, you feel heavy. So what have we confirmed here? We've confirmed that when you are stopping going up and starting going down, you feel lighter. And when you are starting going up and stopping going down, you feel heavier. And remember, heaviness and lightness comes from your force normal, not your gravity. When you feel light, the normal is less than the gravity. And when you feel heavy, the normal is greater than your gravity. All right. That was a lot of information. Let's start processing it with some math. Okay. You have a 50-kilogram person that's standing on a scale in an elevator. The elevator is at rest. The scale would read blank newtons. So since the elevator is at rest, that also means you are at rest. So that just means you're in equilibrium. So your force gravity is what your force normal is. They're equal to each other. And for the scale is a measure of not your gravity necessarily, but it's the normal. It's what you're feeling. Okay? So since you feel your normal body weight, your force normal, which is what the bathroom scale will read, is really just your force gravity, which is really your mass times g, which we know is 50 kilograms times 10 meters per second squared. And so that means you would feel 50 newtons. That's your normal body weight. So when the elevator is in equilibrium and you are in equilibrium, you will feel and weigh your normal body weight. I'm sorry, that should be 500. 500, excuse me. But the same thing applies. You will feel your normal body weight. Okay, now, a 50-kilogram person is standing on a scale in an elevator. The elevator accelerates upward from rest at 2 meters per second squared. Okay, the scale would read blank. So, we are told that the elevator is accelerating up from rest. So that's two things there. One, the elevator is accelerating up. So does that mean that the elevator has a positive or negative acceleration? Well, remember, up is positive. So since it's accelerating up, my acceleration will be positive. When it says from rest, that means I am starting. Okay, so we're going to kind of think about that as we go through this example. Okay, so let's start first of all with a force diagram for the person. So we've got my person written as a dot. I've got force gravity pulling down, and I've got force normal pushing up. Okay, so let's first think about this from a logical state. I know I said I was going to use physics, and I still will, but kind of to get the general idea, let's think about it from a logical point of view. You step on an elevator, okay, first floor. Step on an elevator. It's starting from rest. Okay, the elevator accelerates upward. Now, remember Newton's first law. An object wants to keep doing what you're already doing. You, as the person on the elevator, you're at rest. So you want to stay at rest. You don't want to move. But what happens? Okay, the elevator beneath you is pushing kind of up into you. So it's almost like for a couple, moments there, the bathroom scale beneath your feet is like pushing into your feet. Okay, so that's like the scale is going to read a little heavier than your normal body weight. So right away, that's kind of, setting off a little light bulb in my head, in my light bulb, that my scale was going to read something that's greater than 500 newtons. Because 500 newtons is your normal body weight, you're going to feel heavier in this situation. Okay, another way, and this is where the physics part comes, is I'm accelerating upward. All right, and if I'm accelerating upward, that means my force net has to be upward. And so that means the normal has to be greater than the gravity. So I know that my force normal, when it's greater than gravity, I would feel heavier. But let's now look at Newton's second law. I'm going to first write out an equation, and please get in the habit of doing this. Force net in this situation is equal to what? Is equal to force normal plus force gravity. Those are the only two forces in the y direction that we're adding. Now, the trouble with elevators is that students just forget to take notice of signs. You have to take notice of signs. Do not forget that. Okay, what I'm going to do before I plug in any numbers is I'm just going to rewrite some of those things. Okay? Force net. What does that equal? Well, we learned that Newton's second law tells us force net is the same thing as taking mass times acceleration. That's equal to, does force normal break down into anything? No, it doesn't. So we're going to leave it force normal. Plus, force gravity, what is that? Well, it's m times g, right? That is force gravity. So I just rewrote the same equation, but I actually just plugged in some variables that we know. Now what I'm going to do is I'm going to plug in numbers. Remember, if it's asking for what the scale is reading, what am I ultimately solving for? I'm ultimately solving for force normal. That's what the scale will read. That's your what we call your apparent weight, or what you feel like you're feeling. Okay, so my mass is 50 kilograms. Now, what is my acceleration here? Well, remember, it's the acceleration of the net force, okay, or overall. So that would be the 2 meters per second squared. The question you need to ask yourself is it a positive 2 or is it a negative 2? We've already established that it is a positive 2. Why? Because the acceleration is upwards, and we've made up the positive direction. So I'm going to plug in 2 meters per second squared. That is equal to my force normal, which is what I'm going to solve for, plus the mass, again, is 50 kilograms, times the acceleration of gravity. Be careful here. What direction does the acceleration of gravity always point? It points down. And in this problem, and in all elevator problems, we make down negative. So it's times a negative 10 meters per second squared. If I simplify this, and I'm going to simplify it right here, because I'm running out of space. If I simplify that, on the left side of the equal sign, I get 50 times 2, or 100 newtons, is equal to force normal plus 50 times negative 10 is a negative 500 newtons. And so that becomes 100 newtons equals force normal plus a negative, so that's just minus 500. And now I'm going to add 500 to both sides to end up getting that my force normal is equal to 600 newtons. And that makes sense because we already knew that we should weigh more than what our actual weight is. So when our force normal is greater than our force of gravity, we are feeling heavier. Okay, let's look at this. Now you're in motion. A 50-kilogram person standing on a scale in an elevator. The elevator is moving up at a constant velocity. Key thing there is that we're going constant velocity, so I think equilibrium. And so when the object's in equilibrium, that means that my force of gravity is the same thing as my force normal. And since the force normal and force of gravity are equal to each other, and your force normal is what your apparent weight comes from, my scale is just going to read what my force of gravity is, which, once again, is 50 kilograms times 10. Okay, and actually, this should be negative 10, excuse me. So gravity is negative 500, but force normal is the positive counterpart to that. So I want to make sure I'm not confusing you with the signs. This actually is a negative, but it switches around because force normal is the opposite. So my force normal is the 500 newtons. Okay, now let's look here. A 50-kilogram person standing on an elevator. The elevator now slows to a stop going up. So you were on the elevator, you started going up, you went constant velocity, now you're still going up, but you're reaching that top floor and starting to stop. So if we draw my force diagram, I've got my force gravity is definitely pointing down. That always is true. Now, the elevator is slowing to a stop, going up. So going up means my velocity is positive. But I'm coming to a stop, or I'm slowing down, which means my acceleration must be then negative. Okay, remember, the same direction that acceleration goes is the same direction that force net goes. So my force net, since acceleration is negative or down, my force net needs to be down. So when I draw my force of gravity and my force normal, to make it go down, my force net, gravity has to be greater than normal. Okay, so that's the force diagram. Kind of helps us re-emphasize the concepts, but I'm still going to apply Newton's second law. And that is force net equals force normal plus force gravity. Okay, just like we did before, that hasn't changed. The force net is still coming from those two vectors. What's changing is which one's bigger, normal or gravity. Now, before we solve this mathematically, let's just kind of do a little hypothesis here. Is our scale going to read greater than 500 or less than 500? Well, remember, when normal is less than your gravity, that means you're going to feel lighter. So we should know at the very end, our answer should be less than 500. Let's keep that in the back of our minds. I'm going to write that up here, less than 500. Okay, so that'll be a reminder to us to kind of do a check. Okay, it's always good to do a logical check. All right. Force net can be rewritten as mass times acceleration. Force normal is just going to stay that, and force gravity is m times g. Now I'm going to plug in the values that I know. My mass is 50 kilograms. We are told the acceleration is 3.7 meters per second squared. Is that a positive or a negative number? Well, we know that the acceleration is negative because it's slowing to a stop going up. So I need to make sure when I plug that in, it's a negative 3.7 meters per second squared. That is what will trip students up. That's equal to force normal is what I'm going to solve for, plus my mass is the 50 kilograms, times acceleration of gravity. Well, gravity always points down, and in elevator problems, down is always negative, so it's a negative 10 meters per second squared. Let's simplify some of this. So 50 times negative 3.7, let me grab my calculator here. That's going to be negative 185 newtons, equal to force normal. Now, plus 50 times negative 10, we already know that that's plus a negative 500, or I'm just going to write minus 500. To solve for that and isolate force normal, I'm going to add 500 to both sides. And the 500s will cancel out, and I end up getting, I'm going to write it up here, force normal is equal to negative 185 plus 500, or 315. And that makes sense because we predicted at the beginning we should feel less than 500, which is our force of gravity. What students will make a mistake on, like I said, is this. They will plug in the 3.7 meters per second squared, and they will forget to make it negative. They'll put it in as positive, which means they would have gotten a positive 185. And so when they add these together right here, they would have gotten 685. And that would have been incorrect because if you feel lighter, then you need to be less than 500, not greater. So the sign is important in the elevator problems. All right, finally, let's look at this last situation here. The 50 kilogram person is standing on a scale in an elevator. The elevator cable breaks. Remember, that doesn't happen in real life, but whatevs. Okay, the elevator cable breaks and the elevator is in free fall. Shucks. Don't worry, that will not happen to you. It's going to be okay. What would the scale read then? Well, some of you are probably making a guess right now of 0. And you'd be right, but let's make sure you know how to prove that mathematically, because on tests you do need to show work. So we know how to do this. We know that force gravity, okay, is pointing down, all right, and then force normal, quote unquote force normal, provided you're even still on the scale, and you'll understand why that is the way it is in a second, is pointing up. All right, we have to think about what's happening here. You might be thinking to yourself, wait a minute, I don't know what the elevator's acceleration is. Well, let's think about that. Your force net, in this case, is still force normal plus your force gravity. And we know that can be rewritten as mass times acceleration equals force normal plus mass times g. Okay, so the mass of U, okay, is 50 kilograms still. Now, if the elevator cable breaks, no longer now is the elevator bound to a controlled acceleration. It's not connected to a motor anymore that's controlling it. It's not connected to any sort of like big piston underneath it that pushes it up and down. But it's actually just, there's nothing controlling the elevator other than gravity itself. So when it says it's in free fall, what does that mean? It means it has an acceleration of 10 meters per second squared, gravity, which means you also have an acceleration of 10 meters per second squared. And if it's in free fall, that means it is falling or going down, which means your acceleration should be negative. So the acceleration is negative 10 meters per second squared. Now, keep in mind, that's the net force. Now, that's equal to force normal plus, now you've got your force of gravity, which is your 50 kilograms, times acceleration of gravity, or g, which is negative 10 meters per second squared. Now, when I start simplifying some of this, I get negative 500 newtons equals force normal plus a negative is minus 500 newtons as well. And notice what happens. If you add 500 to both sides, okay, everything's going to cancel out. So really, you end up just getting force normal, which remember is how you feel. Force normal equals 0. Okay? So in other words, you don't have a force normal. The elevator is dropping out from underneath you, and that's why you don't feel any weight. Okay? You are feeling weightless. And notice, what were the conditions of feeling weightlessness? It was when your net acceleration was the same thing as gravity. All right, so that's pretty profound. We can actually take that concept into some later stuff that we do. But the key thing that I want you to get is that when you are in free fall, you are going to read 0. One last note that just came to me that will end the video is this. I want you to think about, I'm going to guess that you're probably sitting in a chair right now watching this video. And I want you to think about what makes you feel right now that you have weight. Once again, you might be tempted to say, force gravity, I have mass, I have acceleration of gravity. It's not the gravity. It's the fact that the chair underneath you is pushing up on you. Imagine if I could come right behind you, and I won't, but imagine I could come right behind you and very quickly pull the chair out from underneath you. For a moment in time, you would feel weightless because there's not a surface or a force normal pushing back on you. So what I really want you to get out of this video, other than the elevator situation, is the idea that your weight, your feeling of having weight, comes from your force normal, not your force gravity. And that's going to be important later. So that concludes this video on elevators.